Hey guys, welcome back to another Kubernetes video. Today I'll be talking about topology spread constraints. And this is a continuation on the scheduling series that I've been doing. And we're getting into some more complex concepts now. And this is actually a fairly recent development from Kubernetes. And it was only released towards the end of 2020. So some of the fields you'll see later are actually still in beta, but it is very, very useful if you're trying to set up a production environment and you need to ensure that you have a highly available application where you want to spread your pods across multiple failure domains, including nodes, zones, or regions within your cloud ecosystem. So let's jump into the content. First of all, what do pod topology constraints allow us to do? They control how pods are spread across your cluster. And what does that entail? It means that we can spread our pods across different failure domains like regions, zones, and nodes, as I mentioned, and we specify exactly how we want that spread to work out. So let's have a look at how this actually looks inside our YAML. As you can see on the right, this is the field itself and all of its subfields. First of all, the max skew field is a positive integer value that allows us to determine the degree to which the pods can be uneven across the different failure domains that we have specified, or the particular failure domain that we've specified. Next is the topology key. So this is the label that all of the nodes will have to have that are within our specified topology. So you may have something like region equals region A, region equals region B, region equals region C, and those different labels will be applied to all the different nodes in our cluster. So we'll have 3 different regions that our cluster is deployed to, and there may be multiple nodes inside each of those regions. And that is all then selected for with this topology key. When unsatisfiable is the field that determines how we act when we cannot actually satisfy the topology spread constraint. And there are 2 options. We can either not schedule the pod or we can schedule the pod. So that's kind of self-explanatory. Next, there is the label selector, and the label selector selects for the other pods that we are considering when we are spreading our pod across the different nodes. So we need to take into account the node itself using this topology key field, but if we're trying to evenly distribute the pods, we also have to keep track of the other pods, and that's what the label selector does for us. Now, there are also some optional fields that we can configure as well. The first one is match label keys, this down here. So this allows us to then match additional labels in the other pods, and it is actually ANDed with the label selector if we specify the label selector as well. So it basically gives us the ability to select for additional labels, whereas the label selector is just a single label. Then we have node affinity policy, and what this actually programs a scheduler to do is to either honor the node affinity that we have also defined for the pod or ignore it. Next is the node taints policy. So if some of the nodes are tainted, we have to again tell the scheduler, do we take into account those taints or do we ignore them via our topology spread constraint? And only just, let's use this as the only parameter that we're using to schedule the particular pod. Again, we can honor it or ignore it. Now, that may have been quite a bit of information, so I have a little example here where we're going to run through how the topology spread constraint what might actually work in practice. So on the right hand side here, you can see that we have defined a pod. The max skew that we have defined is 1. The topology key is zone. So what that means is that each of these nodes, 1 through 4, will have a label, and the key of that label is zone, and the value of the label for node 1 and node 2 is zone 1. The value of the label for node 3 and node 4 is zone 2. Then we have said if we cannot satisfy the topology spread constraints, we're not going to schedule the pod. And we see we have a label selector here that matches for foo bar as the label. And you can see up here, we also have that label defined within the pod itself. So how would this work? When we go to schedule our first pod, we can pop that over on node 1, no problem. What happens here is that now we have a skew overall of 1 because zone 1 has 1 pod and zone 2 has 0 pods. So 1 minus 0 is 1 essentially. So if we have another pod, now we want to deploy it, we try to deploy it to pod 2, but our topology spread constraint says no thank you very much, because that would breach our max skew, because we would then have 2 pods in zone 1 and 0 in zone 2. So that has to come over to zone 2 and in this particular case node 3. It can go to either node 3 or node 4. Let's take another pod. In this case, since our current skew value is 0, 1 minus 1 is 0, we can either go to zone 1 or zone 2. So let's just say we decide to go over to zone 2. Now our skew value is at 1 once again. And this means that when our next pod comes in, we can either deploy it to node 2 or node 1. So that is essentially how it works at a fairly basic level. You can obviously get a little bit more complex with these. You can actually combine multiple topology spread constraints. So if we wanted to have a spread constraint for zones and nodes, we could do that too. But I hope this gives you a little bit of kind of insight into how it really works in practice. But let's get back to the theory and look at some well-known labels. So what are these? These are labels that are kind of understood and known by Kubernetes, defined by Kubernetes itself. They're not user-defined labels. First one is region, topology.kubernetes.io/region/zone, and finally kubernetes.io/hostname. So these are what is recommended to use when we are setting up topology spread constraints. Whether you want to spread your pods across a region, a zone, or nodes themselves, these are the labels that you should use. And why is that? Well, the reason is because the first two are actually populated by the Cloud Controller Manager, and the last one is populated by Kubelet. So by using these labels, you avoid the toil of having to add the labels each time you add a node. So it's highly recommended that you use these. And again, yeah, it just takes away that manual effort. You always know that your node is going to have each of these labels, assuming that you are in fact deploying your Kubernetes cluster to a cloud provider. If not, you will still have the kubernetes.io/hostname deployed, but then you're going to have to look at your own strategy in terms of the regional and zone topology keys. It may be the case that you only have a single data center that you're deploying to. In that case, this is kind of irrelevant to you. You can set up your topology spread constraints across the hosts if you like, but you're not going to be able to do it for regions or zones because you don't have regions and zones to work with. Now there's some additional considerations that we can look at. The first one is namespacing. So as we said, we are taking a look at a group of pods and how that group are spread across our cluster topology, essentially. Well, that group of pods have to be within the same namespace. Otherwise, we will not be able to calculate the skew as I showed earlier, because labels are actually namespaced resources, and the labels are what's used to calculate the skew. Nodes without topology key are bypassed, so if we want a node to be included in our topology that we're using for our topology spread constraint, we have to label that node with the topology key we're using, that particular label that's being used to organize or give a logical structure to the nodes. Finally, a label selector should match the pod being deployed. So if we actually jump back to this example here, we saw that we have the label selector that matches label foobar, and we also have foobar as our label inside the pod itself. So what would happen if we went in here and got rid of this? Well, we'd be able to deploy our pod no problem. It would come in as expected, and it would actually be fine in terms of it would be spread out using the rules that we have defined. But then when we go to deploy our next pod, since the skew is calculated based on the label, we may actually end up with a situation where our next pod will come in and be deployed to the same node, and then our actual skew will be 2 in this scenario, but according to the system, the skew is 1, because this particular node doesn't have the label that is being selected for in our topology spread constraint. So we should always include the label that we're matching for in the topology spread constraint in the pod definition itself. Now, on top of specifying topology spread constraints for particular pods, we can do it at a cluster level as well. And these are applied to the cluster by default, and they don't apply if the pod does not belong to a service replica set or stateful set, or if the pod defines its own topology constraints. So if we set up those topology spread constraints within the pod definition itself, then the default cluster constraints will then be ignored. They'll be overridden, essentially. And they are created as part of a scheduling profile. I won't go into too many details on scheduling profiles in this video, but you can think of a scheduling profile as basically a way of configuring our Kubernetes scheduler so that it operates in a slightly different manner to the default settings. Finally, there are actually some built-in default constraints, and this is how the scheduler operates by default. So in the case of particular nodes, we provide a max skew of 3, but if the constraint is not satisfiable, then we schedule anyway, because by default, a Kubernetes user is going to want to be able to schedule their pods and not worry too much about how they're spread out across different hosts. It is a soft consideration, but it shouldn't be a hard consideration by default unless the user specifies otherwise. And the same goes with zones. In this case, the skew is slightly larger, again, to give more room for error. And again, it's a soft rule, not a hard rule. So that is my video on topology spread constraints. I really hope that was useful. If you enjoyed the video, please give it a like and please subscribe. If you have any questions, leave a comment and I'll get back to you, and I will talk to you in the next video.